Okay, so in this section we're going to continue talking about powers of trig functions, and here we're going to deal with products of powers of tangents and secants. So remember that anytime you have tangent squared x, you can replace it with secant squared x minus 1, and anytime you have secant squared x, you can replace it with tangent squared x plus 1. Okay, so on this example here, I've got secant to the fourth x times tangent squared x dx, and I want to integrate that. So what I'm going to do here is, anytime I have a secant power, I can actually write that, if I can write that as a secant power times a secant squared power, then I might be able to let u equal tangent, and then du would be the secant squared that I use to get from this power. So if I take secant to the fourth x and write it here as secant squared x times secant squared x, then notice here the secant squared x dx, that would be du if u is tangent x. So the idea here is to try to get this, the rest of this, in powers of tangent. So what I'm going to do here is I'm going to replace this secant squared x right here. I'm going to replace this with 1 plus tangent squared x. Well, then I can just let u equal tangent x, and that would become 1 plus u squared times u squared. So that would be 1 plus u squared times u squared. And then what's great is this right here, secant squared x dx, is actually du, because if u is tangent x, then du would be the derivative of that, secant squared x dx. So that's just the du. And then I can distribute the u squared through here, and I get u squared plus u to the fourth du. And then I can integrate these with the power rule, so I get u cubed over 3 plus u to the fifth over 5 plus a constant. And then in the last step, go ahead and replace u with tangent x, and I get tangent cubed x over 3 plus tangent to the fifth x over 5 plus a constant. Now another example here is where I can actually use the other trig identity. So, but here's what I have to do here. I have secant fifth x and tangent cubed x. So in that case, since both of these are odd, I would have to factor a secant x out of this in order for that to be an even, and a tangent x out of this in order for this to be an even. So let me show you how I'm going to do that. So I'm going to rewrite secant fifth x as secant fourth x times secant x, and I'll put the secant x over here. And I'll rewrite tangent cubed x as tangent squared x times tangent x, and I'll put the tangent x over here. Then I'll go ahead and replace the tangent squared x with what I have up here, secant squared x minus 1. So I'll replace that. Now what's good about this is now I can let u be secant x, and that way I'll have u to the fourth times u squared minus 1. And then if u is secant x, then du is secant x tangent x dx, and that's exactly what I have here. So obviously, so this is going to work out just fine because they're going to have the du. And then do like I did up there, distribute. I get u to the sixth minus u to the fourth, then integrate that using the power rule, and then at the end go ahead and replace u with your substitution secant x. And so you get secant x to the seventh power over 7 minus secant x to the fifth power over 5 plus a constant. I've got another real short one down here. This is just how you integrate tangent squared x dx. So basically, if you just wanted to integrate tangent squared x, you could just replace that with the identity secant squared x minus 1, and then you could break this up into two integrals, one integral being the integral of secant squared x, and the other being minus the integral of dx. And then you can integrate secant squared x, you just get the tangent x, and when you integrate dx, you just get the x. And of course, that's a minus, so it'd be minus x. And then don't forget to add your constant. So tangent x minus x plus a constant would be that example. Now the next one is fairly extensive, so buckle your seatbelt on this one. Okay, so what I'm going to do here is I'm going to use parts integration. And so let me show you how I'm going to rewrite that. Let me add a little something here for you. So what I want you to do is I want you to think of this secant to the 5th power of as secant of x cubed times secant of x squared, and then of course the dx. Now then that way you can see how I'm going to break this up. So what I'm going to do is I'm going to let u equal the secant cubed x, and I'm going to let dv equal the secant squared x dx. And with parts integration, I know if I integrate this, this will integrate nicely to tangent x. So I know that'll work out real good for my integration. Now, so if u is secant cubed x, well, du would be the derivative of this. So now this is going to be 3 times the secant squared x, and then times the derivative of secant x, which would be secant x tangent x. So you end up with 3 secant squared x times secant x times tangent x, which ultimately becomes 3 times secant cubed x tangent x, and then of course the dx. And then of course when you integrate dv here, you just get the tangent x. Okay, now doing the parts formula, you have uv, so that'd be the tangent x times secant cubed x, then minus the integral of v du. So if you take the tangent x and multiply it by the du, you actually will get 3 secant cubed x tangent squared x. So I moved the 3 outside the integral, but notice I have the secant cubed x tangent squared x here. Okay, now what I'm going to do next is I'm going to replace tangent squared x with the identity secant squared x minus 1, and then I'm going to go ahead and distribute this. And so when I distribute this, I get minus 3 times the integral secant 5th x, and then plus 3 times the integral secant cubed x. So if you distribute this through there, you actually get secant 5th x minus secant cubed x, and then you're multiplying it by minus 3. So you're going to get minus 3 here, secant 5th x, and then plus 3 times the integral of secant cubed x. Now, remember, all of this is equal to the original integral here. Integral of secant to the 5th x. Alright, but I want you to look right here at this term. Notice this integral is actually minus 3 times the same integral I have on the left. So what I could do here is I could actually add 3 of these using that foldback rule I mentioned earlier. I could add 3 of these to both sides, and that way I would get 4 of those integrals over here, and then this one on this side would cancel, so I would only get these 2 terms remaining. And so then if I divided everything by 4, if you divide this by 4, you get tangent x secant cubed over 4, and if you divide this by 4, you get 3/4 here, and so I would get 3/4 there, and times this integral here. Okay, so now the question is, how do I deal with this integral? Well, I'm going to deal with this integral again using parts. And so this is where it gets nasty, so because I have to leave this and go down here and integrate secant cubed x. Well, here I can let u equal secant x and dv equal secant squared x dx. So again, I'm thinking of this as secant x times secant squared x dx. And then if you do that, then du would be secant x tangent x, actually be secant x tangent x dx. And then when you integrate dv, you get tangent x. So to make a long story short, you apply the parts formula there, and the uv would be the secant x tangent x, and then minus the integral v du. If you multiply v and du together, you get the integral secant times tangent squared x dx. And then to evaluate this integral, you can replace the tangent squared with the secant squared x minus 1. And now let's see what happens when we do that. We bring down the secant x tangent x here, and then distribute the secant x through here. So I get secant cubed x minus secant x here. Okay, now remember, all of this is actually supposed to equal this integral here, the secant cubed x dx. So let's bring it down. So I'll bring this term down, put it there, And then when I bring this down, I'm going to break it up into two integrals, so I get the integral of secant cubed x distributed in a minus through, so it'd be minus that integral. And then I have a minus times a minus here, so that would be plus this integral. Now I can do that little trick again. Notice that this integral right here, this integral here, is actually the same as this integral over here. So if I added this integral to each side, I would get two of these integrals, and then of course it would eliminate the middle term here, and I would just get these two terms here. Alright, then I can divide both sides by 2 to solve for this integral. So I get secant x tangent x divided by 2, and if I divide this by 2, I get, a 1/2 here. And then there's a formula for integrating secant x, and it's actually the natural log of the absolute value of secant x plus tangent x plus a constant. Now, remember, this is where we were earlier, right? So we were here, and now I needed to figure out what this integral of secant cubed x equals, and I've got that right here. So go in and replace this. So here it is. So I replace it there. And then the last step, just go ahead and distribute the 3/4 through each term and add your c, and you got your final answer. And so that, like I said, that one was pretty extensive. And there's also a practice problem down there if you want to do another one that's similar to this. Okay, so if you have a cosine and cosine, or cosine and sine, or sine and sine, using different angles, like right here I've got cosine and the angle's 5x, and here I have cosine angle's 3x. Well, you can actually use this identity. Cosine ax times cosine bx is 1/2 cosine a minus bx plus 1/2 cosine a plus bx. So actually, I can write cosine of 5x times cosine of 3x as 1/2 of cosine of 5 minus 3, which would be 2x, plus cosine of 5 plus 3, which would be 8x. And then you can just evaluate each of these cosine integrals separately if you like. And so when you integrate this, you get sine 2x over 2 times 1/2, so you get sine 2x over 4. And then this, you get sine 8x over 8 times 1/2, so you get sine of 8x over 16 plus a constant. Okay. Now on this one, it's just a similar identity. Here you have sine 3x cosine 5x, so you use the identity sine ax cosine bx, and you can see I've written out the identity there for you. And so to integrate, so you have to rewrite this. So sine of 3x times cosine 5x would be sine of 3x minus 5x, which would be sine of minus 2x. And then sine of 3 plus 5x would be sine of 8x. Of course, the 1/2 I moved outside of the integral on both of these. So then you can integrate this, and you get you actually get minus cosine here, and let's see, you get a minus cosine here, and you get a plus cosine here for the second term. So I think I turned these around. If you integrate sine of 8x, you actually get minus cosine of 8x over 8, and then you multiply it by 1/2, and you get minus cosine 8x over 16. And then when you integrate here, you actually get minus cosine of minus 2x over minus 2x. And so when you multiply the minus times the minus, you get a plus. So not over minus 2x, but over minus 2. And that should be cosine minus 2x there. So anyway, that's how you could evaluate integrals that involve products of sines and cosines with different angles. And at the very end here, you see there's another identity here. You know, had you had an example that involved the product of a sine of an angle and sine of another angle, but I didn't have that case. I didn't work that case. But if you do have that case, then there's your identity that you would use.